So, good morning everybody. This is lecture 1. First, it's related to functions of the building. So, what are the functions of buildings? As you can see, this first thing is it must provide a safe shelter, structurally safe, all right, and desired spatial environment within the space, right, for any human activity. For example, this is a classroom. So, this is what is called teaching of readings, teaching of readings. So, it must have good acoustics so that you can hear, must have good visual environment so that you can write, right, and of course, comfortable from thermal point of view. It is one of the most important thing, right, thermal point of view. So, for that human activity here is teaching of reading, right, which means teaching, learning, interaction. Okay. So, that is what it is. So, building must therefore provide safe and comfortable environment, internal environment against existing external and unwanted internal conditions for a given human activity. Now, what is external condition? For example, high temperature outside, lot of humidity, relative humidity high. So, I must have a comfortable environment against such kind of external perturbation. Similarly, noise outside or noise generated within. So, it should be comfortable against such a thing, but obviously safety is most important, and building must accomplish all this economically. We normally one would be talking about life cycle cost in this context, but anyway cost is not an issue in our right. So, first to talk about safety, which you have learned through your undergraduate programs. Is it safe against all kind of natural forces, right, safe against natural forces such as gravity load. First of all, gravity, like if you have to stand somewhere, your own weight would be there. So, gravity load, snow load. So, many of them are vertical load, wind, rain, etc. Wind and earthquake, they also contribute to horizontal loading into the building, impacts and so on, right. Because of human actions, load can also be there. So, if I show it schematically, there are many of them are gravity loads, most of them are gravity load, and there could be horizontal load as well because of earthquake and wind, and it must be safe against all these forces. So, that is what we are saying. So, that is the safety, and we are not discussing this in this course. Safety is not, already you have so much of elaborate understanding of the same. So, we will not discuss this. So, building interacts with surrounding environment, and that is what we are looking here. And you have humidity, air motion, as you can see, noise, lightning, pollution, rain and snowfall, precipitation as we call it, sunlight, air temperature, solar radiation and all that. So, as you can see, these are the arms, as you see, building is at the center, it interacts with all those environmental factors outside. So, to start with, we will discuss these environmental factors, how we account for them, how do we quantify them. How do we quantify them, any measurable item, how do we measure them? Because in technology, science and engineering, basically technology is science based engineering, right, not empiricity would like to reduce. So, we would like to model effect of air motion onto the building, we are looking at the comfort, not the loading part of it, right. Similarly, effect of temperature outside, heat transfer into the building and so on. So, therefore, in order to do that, we must quantify them. We generally mathematically generalize physical system models. When we talk about mathematical modeling, we generalize it, basically it is a mathematical generalization. So, that is what we like to do, and therefore, we must look into each of this one, how we measure them and how do we quantify them, right, in physical or terms of maths and physics. Let us see. So, comfortable environment, it must be comfortable against external temperature, relative humidity, moisture ingress, condensation, etc., right, and must be comfortable against man-made, external and internal, external as well as internal red colored. So, it must be comfortable against man-made external and internal agency causing discomfort. For example, noise. Besides microclimatic changes are, I will tell you what is microclimatic changes. For example, you change the your activity, human activity, a lot of building, they will change the thermal conditions surrounding the building. So, we will talk about that later on. So, examples, if I say external temperature, humidity, solar radiation, occasional perturbations such as heavy storm, rain, gust, these are external. Man-made, internal, external noise, accidental initiation of fire, which I am not discussing again in this course, generation of waste, odor, fumes and gases, etc. So, these are man-made things, they can cause discomfort, right. Okay. Then desirable internal environment may require provision of adequate visual condition through proper lighting. So, these are desirable condition, and desirable internal also may require reliable proper circulation of human movement and materials. Space, this is an architectural issue, again we are not discussing here. Circulation space, comfortable, ergonomics, even space between two rows, minimum distance between two rows. So, we are not talking of this in this class, except for in case of auditorium design, we will talk a little bit related to this. So, that is kind of introduction what we will have. Now, as I was telling you that we will look into the environmental features which we like to quantify and in terms of some measurable items. So, temperature is one of them. First is the temperature. So, we are looking at the thermal aspects. So, thermal environment, temperature is one of them. Now, temperature, how do we measure? We will come to that. Next one would be relative humidity, air motion, air velocity, speed and direction, these are important, solar radiation, these are all related to thermal comfort. Then precipitation or rainfall, because that is what causes relative humidity change significantly, and sunshine hours, how many hours sunshine is there. Then sky brightness is related to daylighting, sky brightness is related to daylighting. So, these are the features of environment, and based on this kind of features we actually classify climate. So, climate is climate classify or group the whole globe into several climatic zones, and then zones in a given region also, we will talk about that a little bit later. So, these are the features based on we define them. Let us see how do we measure temperature. If you want to measure air temperature, is measured in what is called Stevenson screen. Now, do I have a diagram of this? If I do not have, I will just draw it for you, no problem. It is like a box, it is simply like a box, you might have seen, and it will have louvers, right. So, it is a closed box, so that direct sunlight does not come in, wind does not affect their air motion, there is no air velocity, significant air velocity inside, it remains dry, there is no rain coming into it, protected from the rain, and you measure what you call dry bulb temperature inside. So, what you measure is a dry bulb. For example, if it is a thermometer, well, there are varieties of measuring devices. Liquid thermometers are well known, mercury thermometers, where expansion of mercury, because it has got a linear expansion, or expansion does not vary with the temperature itself, rate of expansion. So, temperature change, volume change per unit temperature will remain constant over a very large range, that is why mercury is used. Some cases alcohols are used. Then there are other things like what you call platinum resistance thermometer, because resistances changes with temperature. I am not discussing them. You have a I believe some of you might take a course on lab. So, in laboratory class they might discuss this. Thermocouple is very popular. What is a thermocouple? You have a hot junction and a cold junction, and if you put this two dissimilar metal, when you connect them together, there is a potential difference that would exist, or alloys. You can understand that, for example, different metal will have different tendency to lose electron. So, if alloys will have similar sort of thing. So, if you connect two dissimilar of them, momentarily there will be a current flow, because there will be a potential difference existing between the two. But if one of the end is at high temperature and another is at lower temperature, so there is a potential difference generated between these two. Now, this potential difference is a function of the difference in temperature between hot and cold junction. So, thermocouple works in this principle, but then again voltage EMF generated per degree centigrade must be constant. So, every type of thermocouple will have its own range of measurements. For example, copper constantine, chromel alumel, platinum and platinum rhodium thermocouples. So, these are used basically for measuring temperature. Thermistors, there are several other measurement devices. So, we are not going in details into this. So, the unit is of course degree centigrade, it is not degree Kelvin, it is Kelvin, simply Kelvin written in absolute scale of temperature. So, this is one thing, this is how we measure temperature. Now, relative humidity, what is relative humidity? Okay, let us first define relative humidity. I think I will come to the algebra part of it later on, but I think I have not defined. Yeah, you see the air is nothing but a mixture of, let me go back to this and write it here straight away. Air essentially is a mixture of nitrogen, oxygen, carbon dioxide, little bit of argon, right. I think it is AR, argon, not Ag, Ag is silver. So, little bit of argon and obviously moisture vapor, right. Now, this is around 78%, as you know, 21% or whatever it is. I am not really interested in this, but I am interested in this part. Now, it forms a kind of gaseous phase solution. So, this is the vapor, moisture vapor, and this moisture vapor has got an importance related to thermal comfort. As we shall see later on, the body would like to maintain a fixed temperature, right. Deep body temperature has to be constant. So, if outside surrounding atmosphere is warmer than the deep body temperature, it would actually heat flow would occur from outside to inside, but then body would like to reject it. We will discuss this mechanism sometime later on, but one of the mechanism is losing by evaporative cooling. So, for example, in the skin, moisture in the skin, if it evaporates, latent heat of evaporation will be taken from the skin itself and it will cool down, the body itself it will cool down. So, therefore, relative humidity or moisture content in the surrounding environment is important, because if it is dry it can absorb a lot of moisture. If it is already saturated, because it is a kind of a solution, as I said. So, there is air has got a capacity to absorb moisture vapor, and this is a function of temperature itself. Higher the temperature, it can absorb more moisture vapor. So, relative humidity is related to that. Relative humidity is a kind of measure, it is a capacity for the surrounding environment to absorb moisture. So, we talk in terms of we talk in terms of relative humidity, we talk in terms of moisture content, that is, if I denote it by phi, it will be moisture content G, sometime we denote it by G, moisture content we denote by G, as we shall be doing in this class, divided by Gs, saturated moisture content at that particular temperature. That is how we define. So, relative humidity we define this. Now, how do you define partial vapor pressure or partial pressure of two gases? Supposing I have two gas and I individually it occupies a volume V, gas 1, the pressure is P1, and second gas which occupies the same volume, its pressure is P2, right. Now, when I mix them together, same mass of the two, and mix them together and put in the same volume, the total pressure will be sum total of this one. You can understand from basically kinetic theory of gases, because pressure is nothing but molecule hitting the boundary of the vessel. When I pack them together, two gases, obviously they will exert more pressure. So, partial pressure is the pressure of the gas in a mixture, which is the pressure when it occupies the same volume as the mixture itself. So, P is P1 plus P2, partial pressure. So, in case of air, partial pressure of air per partial pressure of vapor is the total pressure, right. Now, if relative, if the G is more, moisture content is higher, this will be also higher. So, I can relate these two, partial pressure, vapor pressure as we call it, to the relative humidity. All right. Let us see how do we do it. Let us see how do we. So, partial pressure will be written like this, and we treat them as ideal gases. So, P A, let us say it is only the dry air, V A is equals to the mass of the air there divided by molecular mass of air R T. Similarly, for vapor I can write in the same manner, and both of them are occupying same volume by definition. So, G is mass of the vapor divided by mass of the dry air, that is how we define the moisture content. This will be simply from this one it follows, right. So, G is mass, so this divided by this, and therefore, it would be this divided Pb Mb divided by Pa Ma, right. V will cancel out from both the sides, this will also cancel out because temperatures are same, right, and this universal gas constant because already we have taken N into account. So, this value molecular mass of water is 18.02 and molecular mass of air is 28.96. Now, how does it come? Because nitrogen we know is 28, 0.78 multiplied by nitrogen molecular weight of nitrogen, because it occupies 78% is a 78% is a nitrogen. Oxygen we know 21% or whatever it is. So, when we sum them up I get 28.96. So, this therefore, Pv by Pa comes in, and Pa is nothing but atmospheric pressure minus vapor pressure. So, you can see that moisture content is a function of vapor pressure and 0.662. So, it is actually can be related to the vapor pressure of air, right. Okay. Now, there are some empirical. So, relative humidity is G by Gs, saturated moisture content at saturation for the same temperature. So, there are some empirical formulae, maybe I will solve a problem sometime, but there are other ways of finding this out also, phi, G etcetera. It is through psychrometric chart. I will come back to this sometime later on. This is called a psychrometric chart. A psychrometric chart is one where in this direction here you have got dry bulb temperature dBT. You may not be able to see this very clearly, there could be difficulties, but my intention is not to show here or read it here, but you must be familiar with it, because you can refer to this in SP 41 or any book of the reference that I have given, Marcus and Morris, Kenigsberger and so on and so forth, IHB guideline, ASHRAE handbook and so on, many places you will find it. Now this axis is dBT, and this is from -10 to I think it is plus 60. So, over this range, this particular graph is, I mean it is there for various ranges, some will have up to 30 or whatever it is. So, this dBT is along this direction. This direction is the moisture content in kg per kg, absolute moisture content kg per kg. Now, this is the saturation line, this is the saturation line, this is the saturation line, this is the saturation line. So, if you know dBT, if you know moisture content, relative humidity lines are, relative humidity lines are, this is saturation line, this is 90, 80 etcetera, etcetera. So, these are relative humidity lines. So, you can actually, if you know the moisture content, relative humidity value, you can find it out from there. Also, there is something called wet bulb temperature. How do you measure relative humidity? Then it will come. Now, these curves can be fitted into an empirical equation as I said, and you have vapor pressure is given as saturated vapor pressure minus some constant into atmospheric pressure T minus T W is called wet bulb temperature. I will just define what is called wet bulb temperature, and some again as I said empirical formula is given PSB and PS at any temperature, what is the saturation pressure, those are values are empirically obtained. Maybe I will solve a problem sometime, that will be clear. I will come back to this later on, but let me now define what is wet bulb temperature. Let us see if it is there. Okay, before the mathematics comes in, wet bulb temperature is, supposing I have got a thermometer, right, something like this. Supposing I put a wet cotton here, it is a thermometer, thermometric bulb, it is a thermometric bulb, and I put cotton here, wet cotton here. Another case, I have just the bulb and no cotton or anything of that kind, right. So, I will have the, it could be mercury simply. So, this is dry bulb temperature. Now, where will the, supposing I have got relative humidity 100%, right, where will be this height or reading of this thermometer? It will be same, because this is wet and nothing can evaporate, right. But supposing the relative humidity is low, then what will happen? Moisture from here, from the bulb which is covered with a wet cotton or jute will evaporate, and this will result in depression of this mercury here, which we call wet bulb depression, right. So, this would be somewhat lower. Do you get it? If I have some jute or wet cotton around, wet, it has to be wet. So, they used to have something called whirling hygrometer, where they will have a wrapped around a jute, wet jute wrapped around. Textile mills, very important, many other places temperature, relative humidity is very important. So, they will go on, or in a room where you want to control humidity, they will go on moving around this and then measure the depression of the wet bulb temperature or reading of the wet bulb temperature. The difference between these two is a function of relative humidity. It will be maximum when it will be maximum? When it is 0, it is totally dry environment, it will be maximum, and there will be no depression when the environment is saturated, So, dBT and WBT, wet bulb temperature. So, relative humidity, relative humidity can be measured through wet bulb temperature. There are other techniques like hygrometer, you might have seen. A hygrometer, wheeling hygrometer I was saying, hygrometer measures relative humidity. Earlier days they would use horse's tail, horse's hair. Basically fibers are very sensitive to relative humidity, their dimension changes occur, swell or shrink. So, they would use horse's tail, long one, which will expand or contract depending upon the relative humidity, and this movement can be converted into some kind of analog movement and analog scale and all that. So, we used to have one in the lab of the similar kind. Anyway, so wet bulb temperatures can be measured through hygrometer, and one way is to measure the wet bulb temperature and dry bulb temperature both, right. So, that is what it is. So, that is how we measure relative humidity. Okay. If I have to go to this a little bit, let us go to a little bit of physical chemistry, or you might have heard of osmosis. If I have a semi permeable membrane and I have a concentrated solution on one side and you have simply the solvent on the other side, after some time concentration becomes same on both the sides. Now, this can happen in air also, right. Why does it happen? Because the molecules, the solute will have Brownian movement, and if they collide with the concentration is same on both the sides, they collide with each other and come back to their original. So, concentration doesn't change. Now, do not have much of a relevance here, but still I will just quickly tell you. But supposing I have two columns, one has got the solvent, other has got the solution, and I have a semi permeable membrane in between. I am not drawing the diagram, but just trying to explain you quickly. And if I put a pressure on the pure solvent side, I find that concentration does not change. So that is osmotic pressure. So, concentration gradient can cause movement, same thing with vapor. Concentration gradient. So, vapor concentration, if there is concentration of the water molecule, moisture vapor molecule is less at one place and is high, so there will be movement. So, this is given by fixed diffusion equation, diffusion law. So, this dC is the concentration, dC dx rate of mass flow can be written as some diffusion coefficient into dC dx, and C is nothing but concentration is mass per unit volume. So, if I have rho v C, concentration can be written in this manner. If you remember, we had PV VV was equals to MB divided by MV into RT. So, concentration will be given by VV divided by MB divided by VB. Concentration is nothing but MB by C is equals to MB by VB, mass per unit volume, and therefore, it follows from here PV MB divided by RT, right, PV MB divided by RT, right. So, that is what it is. So, m dot, now I can replace this PV, I can write it like this, diffusion coefficient m dot, combine this equation dC dt. So, you differentiate this with respect to x, this is constant, right, and let us say temperature is constant, then this will be function of simply vapor pressure gradient. So, mass flow is a function of vapor pressure gradient, right, mass flow is a function of vapor pressure gradient. So, the amount of moisture that can evaporate from your body is a function of the vapor pressure gradient as well. So, and this I can add to a frictional coefficient. This is if there is no kind of a resistance, but there is a frictional resistance, then I will just put this mu as a frictional resistant term, and that is how I can write this mu dot, and it's convective. So, convective heat or movement, as we shall see, we will see that the rate can be proportional to this. So, I think we will stop here.